Καλώς ορίσατε. Welcome everybody to this seventh installment of the Kylafis Lectureship. And to start, I would like to invite to the podium the chairman of the board of directors of Forth, Professor Harmandaris, to say a few words.
Hello, everyone. It is a great pleasure to have you here, in particular to have with us Professor Blandford. As you very well know, Forth has a tradition for a number of things. One is academic excellence and providing opportunities to the younger generation to attend and interact with exceptional scientists from all over the world, and also to honor people that have decided to make Crete their home and the academic ecosystem of the University of Crete and Forth their place, and to offer their energy and imagination and hard work to make the place better. And it is with great pleasure that this year, for the seventh year in a row, we honor Professor Kylafis with a distinguished lecture that the Institute of Astrophysics started in 2019. And Nick needs no introduction to most of us. To the younger students of the physics department, we make sure that they get the Nick Kylafis experience. And Nick consistently over the past several years, we pay him extra to do that. He teaches freshman physics to the incoming class. And you have the experience of sort of like getting the rigorous mathematical formulation on how we can apply physics well beyond the big body interacts with a small body, etc. And also we are really honored that Nick, and very fortunate that Nick remains with us, and he contributes with his research, teaching, and often unsolicited advice to the progress of astrophysics in Greek. As you know, Nick did his undergraduate at the University of Patras and then moved on to the other side of the Atlantic for education, and then as well as getting a faculty position at Columbia. And then he decided to come back to Crete and set up, together with Professor Papamastoriakis, the astrophysics group at the Department of Physics. And he was instrumental in actually convincing the state to create the Institute of Astrophysics, which honors him today. And without further ado, I would like to ask Professor Pavlidou, the director of the Institute of Astrophysics, to say a few words both about our distinguished 2025 Kylafis lecturer, as well as for Nick, and I'm sure we will all enjoy a wonderful lecture. Thank you.
Thank you, Professor Harmandaris. Dear friends, thank you all once again for joining us for the 2025 Nick Kylafis Distinguished Lecture. The Nick Kylafis Lectureship was established by Forth in 2019 in order to honor Nick Kylafis, Professor Emeritus at the Department of Physics of the University of Crete, on the occasion of his 70th birthday, for his 35 years of scientific contributions and for his leadership in the establishment and continuous improvement of the astrophysics group at the University of Crete and Forth. This lifelong commitment has been instrumental in the international recognition of the research activities of the Crete Astrophysics Group, which ultimately led to the creation of the Institute of Astrophysics at Forth in 2018. Under the auspices of the lectureship, every year a distinguished theoretical astrophysicist is invited to Forth for a brief visit. Our institute is young, but it is already building its traditions. So this is the 7th installment of the Kylafis Lectureship, and as anticipated, its establishment has resulted to visits by high-profile astrophysicists who have inspired with their presence the younger generations of scientists trained at Forth and the University of Crete, and who have communicated to the wider scientific community at Forth and Greece the latest achievements in the rapidly evolving field of theoretical astrophysics. The establishment of the lectureship is also building towards a different kind of tradition, that of honoring those who have contributed a lifetime of service towards the development and success of our common research home, the physical and mental space where we can all create and thrive, where we can get excited about each other's ideas and rally behind our common banner, onwards and upwards towards unlocking the mysteries of the universe. As our motto says, the sky is not the limit. So, on behalf of all of us at the Institute of Astrophysics, thank you, Nick, for everything. Dear colleagues, dear students, dear friends, I'm both absolutely delighted and profoundly humbled to be introducing this year's Kylafis lecturer, Professor Roger Blandford. Having obtained his PhD in Cambridge under Professor Martin Rees, he served as professor at Caltech for 27 years, moving to Stanford in 2003, where he led the newly minted Kavli Institute for Astroparticle Physics and Cosmology, the now famous KaiPAC. He's fellow of the Royal Society, member of the US National Academy of Sciences, fellow of the Royal Astronomical Society, and legacy fellow of the American Astronomical Society. He is the recipient of the most prestigious awards in our field, including the Helen B. Warner Prize and the Danny Heinemann Prize of the American Astronomical Society, the Eddington Medal and the Gold Medal of the Royal Astronomical Society, the Humboldt Prize, the Shaw Prize in Astronomy, and the Crawford Prize. Yet, merely listing his achievements and accolades miserably fails to paint a fair picture of the prominence, universal recognition, and respect of his peers that Professor Blandford enjoys as a leading theoretical astrophysicist of his generation. When we teach our students the scientific method, we tell them in the beginning there is observation, then a hypothesis, then experiments to test the hypothesis, the model of how the world works, its predictions, and if experiment agrees with predictions, the hypothesis stands. Roger Blandford is the hypothesis. He's a hypothesis generation machine. In the field of relativistic astrophysics, world collaborations are formed, multi-million-dollar experiments designed and built, billion-dollar satellites flown to test Professor Blandford's hypothesis. Models that bear his name and that are taught as such in graduate classes. He's currently serving as a Luke Blossom professor at Stanford and is leading the international Simons collaboration on extreme electrodynamics of compact sources. And this is, in fact, the theme of his talk today, a talk we are so certain will be dazzling that we are prepared to offer our thanks and gifts in advance. So I would like to call Professor Blandford to the podium.
Now, I will start with the as it's not, well, this is the original, you know. If you've seen a movie about Monica, excuse me, anyway, it's a long story, but I digress. Yes, it is the original. I will, even though this thing is recorded, it is with great pleasure that we give the disc of Festus. As you very well know, this is the logo of Forth, and it embodies effectively something unknown, and how academic research actually enables us to solve mysteries that we could not even imagine. Now, this is very rightfully that we offered it to Professor Blandford, because I found out that a distant relative of Professor Blandford actually had a seminal contribution in deciphering linear B. That's what. So even though Professor Blandford lives, I think, on Sunday, we expect that if possibly late Saturday night or possibly Sunday morning, we'll come up with a theory which explains this for us. Following no pressure.
Oh, thank you. Thank you so much. Thank you very much. Thank you very much indeed. Thank you very much. Thank you. Wow. What's this? Good. Amazing.
And we have a couple of other presents that Vaso Pavlidou will offer.
Wow.
It is the diploma.
Yes. Oh, lovely. Yes, thank you. So, I think. Oh, thank you.
Now do you
Thank you.
Just
That's
hold it so that the
yes.
picture, then we take a picture.
Yes. Okay. Yes. Yeah. Hold it like that, please.
And also
Oh.
some
Coffee
coffee tables
takers.
with
Oh,
pictures from
lovely.
Skinnacus. All the
Yes.
all taken from
Skinnacus. Oh,
Skinnacus.
lovely. Okay. Yes. So here we go. Yes. Lovely. Yes.
So without any further ado, the floor is yours.
Oh. Wow. Thanks very much indeed. It's been a great honor and privilege to come here, and I've really enjoyed my time here so far amongst friends and colleagues, and also especially with Nick Kylafis. We were colleagues together in Caltech not so long ago, and we got to know each other then and kept in touch, and so it's really great pleasure to be back here in Crete, in Heraklion, in Forth, and the Institute for Astrophysics. And yesterday I had the privilege of making my first visit to Skinnacus, and it was lovely. And I'm very excited about the future of that observatory. And I'll maybe say a few more words about that. Thank you also for your generosity in these gifts. And I'm not sure I'm up to this, but for the students here, it's a homework problem. I was asked to talk about extreme electrodynamics, and I have the privilege of leading a Simon's collaboration on extreme electrodynamics of compact sources. This, as you will notice, is palindromic, which I think is a word invented, and it's a research collaboration. It's an international collaboration, and there's a lot going on in this area. And what I'd like to do is to try to communicate to you the flavor of some of the research. So this will be, at some level, an overview. Now, there are many students here who may want to dig deeper into some of these problems, and I'll be here for a few days, and I'd love to chat with you, or we may come up in some question and answer if you do that at the end. But I'll give you sort of the top level, as it were, discussion of this, and it will involve some physics, but I'll try to keep this at a reasonably accessible level. So this collaboration, as I say, is on extreme electrodynamics. And so let me just get straight to the point for the physics students here. And you will have seen, if only on a t-shirt, but I hope in a class, Maxwell's equations, which came from the middle of the 19th century. And it was a remarkable synthesis where James Clerk Maxwell here took the experiments by many experimental physicists, including especially Michael Faraday, and was able to make a mathematical description using electric fields and magnetic fields and electrical current and charge, things we're all familiar with in the 21st century. And he produced these equations, which were very, very successful and, of course, led to a lot of industry in the 19th century and much more in the 20th century. We see them in astrophysics, in the Earth's magnetic field, for example, which you know about just sitting on the Earth, but spacecraft know about it going way away from the Earth. We see it, for example, on the surface of the Sun, where here we see a bunch of magnetic field lines. We're kind of familiar with magnetic field lines that are tied to the surface of the Sun like that, and you see these field lines like that. They're illuminated and seen, in this case, in X-rays. and they're enormous. Here's the size of the Earth, for example. And this description of this is at the largest level is using the equations that James Clerk Maxwell first wrote down in this rather mathematical form. One of the implications of these equations was that he could describe light. And that light, as you know, propagates with a finite speed, and that can be deduced, that speed, from experiments performed in the laboratory. And lo and behold, it agrees with what is measured in astronomical and other measurements of the speed of light. And now, what I'd like to make 2 points about this. One is that when Maxwell wrote down this symbol here, J, stands for the electrical current. In Maxwell's description, this current is continuous. It's like a stream of water or something coming out of a faucet. And there's no reference to it having any atomic or components there. And now Maxwell himself contributed mightily to what is called kinetic theory. That is the description of the gas in this room as a series of molecules. He didn't see it as a continuous fluid. He described it in terms of, he didn't know about molecules necessarily, but he did think about it as being made out of smaller atoms, if you like. And he also knew about Faraday's laws of electrolysis. And for those of you who are physicists, this is one of the first hints that electrical charge, what you see coming out of your socket, is carried by individual particles. Now, that didn't actually happen as an experimental discovery for nearly 30 years with the discovery of the electron and so on. But it was very much an idea that must have been in Maxwell's head, despite the fact that he used this description. And of course, soon after the discovery of the electron, we moved on to atomic physics, to nuclear physics, to particle physics, to plasma physics. And all of those are based on synthesizing what you see in the laboratory or in the telescope in terms of constituent smaller particles. And this sort of counterpoint between the Maxwell view of continuous current and so on, and the atomistic view that there's small particles that are doing the job, is one that I'll return to in this talk. So let me go on to the other type of electrodynamics, which is often called quantum electrodynamics. And this is the creation of the 20th century by many people involved in it. Here is Richard Feynman, who created one of the best ways of calculating in this theory. And what he said was, Maxwell said, let there be light. And the physicists of the 20th century, including especially Richard Feynman, said this light is composed of photons, particles of light, if you like. So there's particles. And for the purposes of this lecture, a point I want to emphasize is that electrons in a magnetic field, they are like electrons in an atom, and they have discrete states. They have special levels of energy, and those are what in the case of an atom are responsible for spectral lines, and you get something similar when you have a magnetic field. Now, normally, with weak magnetic fields like the one in this room, this is not a terribly important consideration. But in astrophysics, we encounter magnetic fields that are very strong. And there is one special magnetic field, and it's called the Schwinger field, and it has a strength of 4 gigateslas, that's 4 billion teslas, and one, I don't know whether people here talk in terms of teslas or Gauss or some other units, but 1 Tesla is 10,000 Gauss, and in this room it's about 1/3 of a Gauss, so you get some idea this is an enormous magnetic field that you're seeing. And we see astronomical objects where the magnetic field strength appears to be perhaps as much as 30 times as large as this special Swinger field. So this is regular quantum electrodynamics, the sort that's regularly taught in physics classes. We're taking it into a new regime in astronomy, taking it over this critical field, and there's a whole new type of physics that's coming in there. And this extreme quantum electrodynamics, like the extreme magnetism back here, this extreme quantum electrodynamics is going to require new processes, and this is what you need to describe what you observe with your telescopes. So that's what this lecture is going to be about. Now, what I'm going to do is try and connect and show the breadth of what we're doing rather than the depth of an individual part. So let me just say here, in physics, it is common to say that there are four fundamental forces or types of interaction. One of them is gravity. One of them is electromagnetism. One is what's called the strong nuclear force. This is what holds, for example, protons and neutrons together. And then there's the weak force, which is what involves ghostly particles like neutrinos. And these are distinguished quite commonly by physics. And all of those appear in the story I'm going to sketch for you. All of these four forces. So the extreme electrodynamics is impacting this full range of physics. And I won't explain what these cartoons here are in detail. This is a cartoon of a neutron star, and this is like a Feynman diagram for some of the processes involved. Black holes people have heard about, so this is extreme gravity. Again, these issues come up there. What we're talking about a lot is black holes and neutron stars. So we've seen here two of the main players. This is a description of a neutron star, and you see structure down here going to densities that be 3, 4, 5 times the density of nuclear matter, the density you see in an atomic nucleus. And we have heavy ion collisions, that is the laboratory experiments, and those relate strongly to the observations of, say, collisions of neutron stars. And these are complementary physics here, and so the physics that is discussed in the laboratory there has to be extended to deal with what is coming out of our telescopes. And then there's the weak force, which involves neutrinos. We're seeing these neutrino sources. I'll make that a bit more explicit down the road. And so we see them, and the origins of those sources are assuredly electromagnetic, and we have to have explanations of how those neutrinos are made. And in all of this, you need plasma physics. Plasma physics is saying there are electrons, there are protons, maybe there are positrons, but there are electrons and protons, positively and negatively charged particles, and they don't just behave independently. That electron does something, that proton does something, and they don't talk to each other. They're strongly interacting with each other. And unraveling this, what we call many-body physics, all these strong coupling and interactions, is the challenge in much of this physics. So let me tell you a little bit about our two types of astronomical objects that are engaging mostly my colleagues and myself. Firstly, there are neutron stars. They were in fact first discovered in 1962, although it wasn't totally clear to most of it, except this man who sort of got it right, Rostovsky. But my first encounter was almost fortuitous. I became an undergraduate in Cambridge University in September 1967, and I heard one of the first talks about radio sources that were going tick, 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 tick. They were called pulsars. They were thought to be little green men for a while, I'm not sure too seriously, extraterrestrial sources of signaling or something. And it soon became clear, and here are some of the people who got the idea right, that what in fact they were neutron stars spinning, and the tick, tick, tick was once a day on that neutron star. And the periods of these neutron stars at that time were roughly about a second or so. Now we know of them that are as short as 1.5 milliseconds. So 1.5 milliseconds, that's a pretty short day. And so they now, you see them spin and you see them going tick, 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 tick. And here's a famous astronomical object called the Crab Nebula. A man called Franco Pacini correctly inferred that this was powered by a spinning neutron star. And a neutron star is very small. It's about 10 kilometers in radius. And it's a whole star as massive as the sun, about 10 kilometers in radius. And if you do the sum, which you can do in your head, it says that the density is roughly that of an atomic nucleus. It is very, very dense. And so we have seen them in many other manifestations. We have seen them bursting on the sky in flashes. I'll say a little bit more about that. Some types of so-called gamma ray bursts, I'll say a bit more about those, are seen to be neutron stars. There are a recent phenomenon called fast radio bursts. I'll say a little bit more about those. These are the sort of astronomical descriptions of these objects. And we believe that many of these, perhaps most of them, are associated with neutron stars. Here's something very special. As you will surely know, gravitational radiation has been observed directly. And one of the sources that was seen early on was two neutron stars that spiraled together, lost energy, and merged, presumably to make a black hole. So two neutron stars merged to make a black hole. Here's the signal that was measured using the gravitational radiation detectors. And so we see there the formation of a black hole with a neutron star, and assuredly that is an electromagnetic phenomenon, and we are going to see these sources as with the strong magnetic fields that are associated with them. So there's a lot more going on here. There's periodicities associated with spinning neutron stars and so on. And so you can see that there's a large swath of astronomical observations which are telling us about the physics of neutron stars. So let me say a little bit more about that here. As I said, a neutron star is about 11 kilometers across typically. It has mostly the physics, a very large representation of the large physics subfields that you see in are expressed within a neutron star. In the interior, you can see superfluidity, superconductivity, which has observable consequences. You can see the behavior of metals being expressed in the outer parts of the crust of neutron stars. They have solid crusts. You can see exotic nuclear physics in a regime that is inaccessible to experiment, seen in the center, and we're trying to figure out what is going on at the very center, at the highest density parts of the core of a neutron star. You can see very strong magnetic fields. In the sort of pulsars, the sort that were described in 1967 in the lecture I first heard about them, the fields are about 100 megateslas, about 100 million teslas. The fields that are seen in a subset of these, called magnetars, can be 1,000 times more than that. And that is way over this quantum electrodynamical critical field, taking you into new regimes of quantum electrodynamics. And it could be that in the interior of these neutron stars, the magnetic fields are 100 times larger than that even. So this is taking you into totally new regimes. Here are some of the heroes of telling this story. Some of the physicists here may identify them, but what is remarkable is how much of the range of regular physics is expressed in these outrageous conditions inside and outside a neutron star. So here are just a few observations that we have. These are a bit more recent. I'm not going to go through all of them. I'll just make a few points. Firstly, I said they go tick, 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 these neutron stars, and that's a neutron star with a magnetic field pointing out of it. And imagine that that magnetic field is like looking at a lighthouse. So it's going to send out light, or in this case, radio waves, or in some cases it does send light and X-rays and gamma rays, but we'll imagine radio waves, and you're observing it, and it goes around like that and goes around like that. So every time I rotate on my axis, you see a tick. So that would be a rather slow pulsar. I'm not able to emulate the 1.5 millisecond pulsars, but if you give me enough to drink in Crete, I may be able to try. So at any rate, so you've got this very, very, very good clock. And then all of a sudden it undergoes these great changes, these so-called glitches. And so there's a big change in the period. And what that means is there's something going on in the interior. It might be, in some cases, it might be something like an earthquake. We could call it a starquake if you like. It could be something more exotic, and probably is something in the big cases like this. It could be something more exotic, like a bit of condensed matter physics involving the superfluidity and the superconductivity and its interaction with the crust of ions around it in the outer part of the neutron star. So this is actually a lot of information about the interior. Let's just take this one here. I mentioned that there was one very famous neutron star merger observed by the LIGO and other detectors, where they were able to see two neutron stars come together and make presumably a black hole. But in the process of doing that, where they made this black hole, they also sent out a pair of jets. These are, and I'll explain what a jet is at this point. This is a relativistic outflow from a spinning object like a newly formed black hole. And these two jets, instead of spinning, they go out just like that in opposite directions, with emitting material moving very close to the speed of light. And that makes objects, this is a lot of words here, so gamma ray burst, that makes a type of gamma ray burst, but it also eventually makes radio observations, as we see here. So essentially what was found is these jets go way outside this collapsing neutron star, something 10 kilometers across, and they're going light years across into the interstellar medium. So these jets, and we'll see this theme repeated, a tiny compact object makes these jets which propagate way outside the original source to light years across. We'll see a much larger example soon. I mentioned the fast radio bursts, and they were, I said these are associated by most of us who think about this, probably the majority of them, with what are called magnetars. These are the super magnetized neutron stars, not like the regular neutron stars seen in the Crab Nebula and so on, but ones that have 1,000 times that magnetic field strength, enormously strong magnetic fields. And this conjecture was given a lot of support when a small-scale version of one of these so-called fast radio bursts was seen associated with a known example of these magnetars in our galaxy. And this happened about 3 or 4 years ago, and it was very clear that it was an identification with a source that we knew from quite different arguments was a neutron star in our galaxy, a magnetar in our galaxy. And so that's sort of progress in this business for sure. Here's another example. I remember I said there were jets and they come out from compact objects. And here's another example. This is a pulsar. In fact, the same thing is seen, is rather like the Crab Nebula, and the same thing is seen in the case of the Crab Nebula. And this makes this spinning pulsar. It's in a nebula called the Vela Nebula. It makes two jets like that go out for tens of thousands of years. They go out for tens of thousands of years in opposite directions. And I'm going to explain how we think they are actually made by a tiny neutron star or a black hole at the center, similar mechanisms at work. And then a recent discovery, which happened about 3 or 4 years ago, is that in this source you can measure X-rays, and in particular those who know what this means, measure the polarization of those X-rays, which is enormously high. And a satellite called IXI was able to do this. And the bottom line here is that surrounding this nebula on scales of hundreds of light years, there is a giant flow of electrical current. So this little tiny generator, 10 kilometers in radius, is able to produce an electrical current, in this case of about 10 to the, I would say, a million billion amps, is able to create that electrical current, and it goes all the way out into the nebula and creates this pattern of polarization. So these tiny little neutron stars are generators of current, and by Maxwell's equations, generators of magnetic field. And this is a theme that we're getting used to, that these tiny generators are making enormous, large-scale magnetic fields and currents. Going on to black holes. Yeah, these are black holes. These are just some cartoons. This is a quasar. People have heard of quasars. They're the hyperactive nuclei of galaxies. And they outshine the galaxies, sometimes by a factor of 1,000. They too create jets. This is the first quasar identified as such. It is called 3C273, a rather forgettable name. And these are the two gentlemen who were involved in the discovery. And they create this jet of stuff that's moving out here very fast, almost at the speed of light, and is created by a tiny black hole in the center of that galaxy. In this case, the black hole is about the size of the solar system. It's very small compared with the galaxy. And yet it creates this jet that goes way outside with electrical current probably along it and large-scale magnetic fields. Here's a famous image that has been, and I'll come back to this a little bit, of a larger black hole in the nucleus of a galaxy called M87 in the Virgo cluster that's relatively close by. And there's been a lot of reproduction of this image and subsequent ones. And what you see here is the shadow of a black hole. Using radio millimeter telescopes all around the world, you're able to resolve on the smallest scale the image around the black hole. So in here there is a black hole with a mass of 6 billion times the mass of the sun, surrounded by emitting gas, and that black hole is responsible for retaining this gas and also creating jets, rather like this one here. I said the gamma ray bursts, I introduced those, not the fast radio bursts, but the gamma ray bursts. They derived back to the 1960s when they were first discussed and first found, and they were discovered by satellites looking for illicit nuclear explosions. And for a while they wondered what they were looking at, but it soon became clear they were looking at cosmic phenomena, these gamma ray bursts. And we now know that the sources of these bursts of gamma rays, which happen about once a day, and they're short, very short flashes lasting a few seconds of gamma rays, they're seen across the universe. You're seeing them from the other side of the universe. It's quite remarkable. And so here's an early compilation. We know much more than this. It's 2,000, 3,000 or so. And here's another type of black hole that is seen. This was observed in 1972. It was shown to be a black hole with a mass about 10 times the mass of the sun in orbit about a regular star. And by careful spectroscopic observations by these people who I knew when I was a student, they were able to show the velocity of the orbit and infer that this was the first demonstration that black holes actually existed in astronomy. They weren't just a general relativist imagination, but they really existed in astronomy. That was, I think, taken seriously by the community. And then in retrospect, they went back to say, oh, maybe these quasars and M87 and so on, they too are powered by black holes. And around about this time, people became to accept very strongly that the nuclei of galaxies and the companions of regular stars and some binary systems in our galaxy are indeed black holes with all of the wonderful and mysterious properties they have. These discoveries, observational, and to some extent, mostly observational and experimental, were two sets of Nobel Prizes were associated with this. And I won't go into any more detail about that, but I will say a little bit more about, again, about the theory here. The description of black holes, there are many people who followed up the early mathematical description of a black hole using general relativity by a New Zealander, Roy Kerr, then John Wheeler and Roger Penrose and Stephen Hawking, household name. They and many others were able to elucidate their structure and their properties, and we now know that they are essentially, we have now, using the mathematical description devised by Roy Kerr, this is the description that describes essentially all astronomical black holes. And if you take the febrile imaginings of a theoretical physicist, you can invent other types of black holes, which are very important to think about because they teach you about physics. But the ones that astronomers observe, this is all you really need. They're surrounded by gas, like this, and this is a sort of simulation, of course. And here we have the so-called event horizon. This is the surface of no return around the black hole, so don't go there. And then surrounding this is a region, if the black hole is spinning, called the ergosphere. And I'll say a tiny bit more about this. The key thing about the theory here is that if the black hole is spinning, and typically we expect them to be spinning, they aren't just a source of gravitational energy. So if I just drop an apple onto the floor, I get some energy out, as Newton might have done. But in addition, there is spin energy like that associated with a spinning neutron star, which is powering the Crab Nebula. A black hole can do the same trick. Just like the neutron star in the middle of the Crab Nebula, it can illuminate its surroundings. And this spinning energy can be extracted using magnetic fields. So we have very strong magnetic fields. And I'll return to this point, but we have strong magnetic fields. They are attached to the event horizon of the black hole, this surface of no return, and they are instrumental in extracting the spin energy from that black hole and illuminating the sky to the gratification of astronomers and newspaper readers and everyone else. So this is, and here, I think Rashid Sunyaev was an earlier Kylafis lecturer. So those of you who are veterans of Kylafis lectures, remember Rashid. In fact, I just spent some time with him last Sunday, so very much on my mind. Okay, so there we go. There's the black holes, and so there's rotational power there. And here's, just like I did with neutron stars, here are some recent observations. So my point in showing this is to say this is a very active field. It's discovery rich. Things are happening on a timescale of months or years. We're not waiting for the key experiment 30 years down the road. This is happening on a very short time scale. Here are recent observations of that black hole in M87. There are jets associated with it, and we can see these jets coming out. Here is a source that I'm very keen about. In fact, this is the source I was discussing with Rashid Sunyaev when I met him on Sunday. It's called SS43. It's a galactic binary X-ray source, and it has a black hole and a companion star, and I think we now have very good evidence that that black hole is orbited by a third star, and that third star is responsible for the precession, for the jets themselves. They don't just go out like that. They actually process around like that, just like you might see in the top. This is remarkable, and astronomers have been trying to understand how nature performs this trick, and I think we now know. So that's kind of interesting. You can make images of it, and you can see it in the Doppler shifts of the spectral lines. Some of these sources are high-energy neutrino sources and gamma ray sources. So here's one that's claimed to be. We also see, quite probably associated with black holes, but not necessarily, if there are alternatives, we see cosmic rays. And cosmic rays, they're seen on Earth. There's about one cosmic ray going through your body every millisecond or so. So I don't want to frighten you, but it's okay. But if you were out on the moon or Mars, you should be a little more worried, and this would be an issue. And these cosmic rays have a range of energy, and the most energetic of these cosmic rays, they're individual particles, probably something like silicon nuclei, and they have the energy of a well-hit soccer ball or tennis ball. So think about that. This is one tiny little atomic particle, subatomic particle, and it has that energy because it's moving so fast. And this is one that was measured a couple of years ago. Here's another phenomenon that was seen. You may have seen about this in the newspapers in the last year or so, is the probable detection of black holes merging together in one form or another. And what they do is they merge together like those two neutron stars I showed you. Remember the two neutron stars I showed you? Big black holes can do this as well. And they can make a background of gravitational waves, which is seen not by the regular detectors, but instead is seen by pulsars. These pulsars are such good clocks that by measuring how the frequency of the pulsar changes, these pulsars can be used to detect gravitational waves that are propagating through the interstellar medium between the pulsar and us. So there's a pulsar there, tick, 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 tick. There's a radio astronomer here with a telescope saying, I'm measuring those tick, 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 ticks. And the difference is caused by the intervening gravitational waves, which you can measure. And now with a lot of heroic work, radio astronomers have been able to measure this effect here. And so they see a background of gravitational waves. And then in a parallel investigation that I've been talking with my colleagues here about, there are observations of periodic variation in seen in the nuclei of galaxies. And in this case, it's a source which has 9 periods of oscillation. And we believe that these are binary black holes, the sort that will eventually produce waves like this, but they're essentially the parent population that are making the waves like this, and eventually in millions of years they will merge. And so we think we are starting to see the first instances of individual sources that are responsible for this background of gravitational waves, which has recently been detected. So this is very much a field that's moving fast. We make some mistakes and so on, but it's very, very interesting what's going on. So there's a lot happening here with black holes. And then I said SS433, I've forgotten I put this slide in here. This is something that I said I'd draw attention to Rashid Sanjayev. He has just written a paper with his group using a telescope called the Rosetta, X-ray telescope Rosetta, showing exquisite detail about SS433. And these are very high energy gamma ray sources. These are X-ray observations. And so we've learned a lot more a month ago about this particular source, which is one of the sort of poster children, if you like, for stellar mass black holes in our galaxy. So those are just some of the flavor of the observations that are going on. So I said I'm just going to give you a broad brush of the range of this. And I'd like to switch gears a little bit and talk about the sort of methodology here. And this is I think a good case history. There are I mentioned the gamma ray bursts that were seen by satellites that were put up there to look for illegal man-made nuclear explosions, and what they found were these cosmic sources. And in the early days of this business, my colleagues who were very creative came up with hundreds of explanations. I think there were probably over 250 published. This is published explanations of what was going on. And there were many crazy ideas out there. And it isn't as though they all give an equal time today. We now know that the whole class of gamma ray bursts is probably one of three totally different cosmic phenomena. The first one is that there is a magnetar there, and there is an explosion there is a magnetic, like a solar flare, a magnetic rearrangement on the surface of the magnetar. That's one of them. The second one is that there is a type of supernova explosion where a massive star collapses, the center cannot hold, and there's a black hole that forms in the middle, and it squirts out two jets that make the gamma rays that we observe. And the third type is the one I've already given an example of, is a neutron star merger. So here we've got two neutron stars merging. These are the so-called short gamma ray bursts, and this makes a black hole too. So these are the birth cries, if you like, of gamma ray bursts. And these are three quite distinct mechanisms. And all the other ideas, that's for somebody else. That's something rather different. So we have made a lot of progress in interpreting these objects. So that's kind of interesting. Now, the fast radio bursts, I said there were gamma ray bursts. These are the things seen in the 1960s. The fast radio bursts were first discovered about 18 years ago. And again, these were not gamma rays, but radio waves. So you've got a rapid pulse of radio waves, and some of them are maybe millisecond, some maybe even a microsecond in duration. And there were many explanations there, and I'm not going to go through all of these. We had the same sort of story of everybody coming up with creative ideas, and it now looks like probably the majority of them, not all of them, I'm sure, but probably the majority are these so-called magnetars, these hypermagnetized neutron stars with these enormous magnetic fields. And so here are examples of these. So we see these pulses of radio waves, and they're now seen almost exclusively in radio waves. And so you see these pulses of radio waves, and again, they're coming from right across the universe. We see them right across the universe, and it's some tiny magnetar with an enormous magnetic field, 10 or 11 kilometers in radius, and it makes a flash like that, and we see it in our radio telescopes. So these are remarkable things, and they're also, of course, very useful. And they're useful for cosmology, for example, because you're seeing these radio waves crossing the universe. This is very useful for learning about the large-scale structure in the universe, and that's happening. And so there's a lot going on in this business. Again, and we're learning a lot about it, and there's a lot of argument going on, particularly with my collaborators, as to how these radio waves could be made in a magnetar. So here's my version with a nod towards early Greek scientists, including Aristotle and his predecessors, with earth, air, fire, and water. So the normal, most in outline, what we think we're looking at is some sort of star quake on the surface of the neutron star. We can argue about how that happens. It's some disturbance. There are various ideas about this. And so here's a terrestrial version of this. So we have a star quake, and then that makes a magnetic wave. You shake this magnetic field around, so it sends a wave right out into the region outside the neutron star. Enormous magnetic fields shaking around like that. And this is a bit like Harrison Ford with his whip there. As you go, as the whip eventually cracks, it becomes almost supersonic at the end. So the whip cracks. And what is happening is the energy is carried by less and less whip in that case. In this case, we've got the energy carried by less and less magnetic field. So that makes something analogous to that cracking sound of the whip. And that would be the fast radio burst. It clearly involves electrical currents. So here's lightning here. And then what you end up with something is a concentrated release of electromagnetic energy that is really rather like a tsunami. And of course, people in Crete are historically, and in terms of contemporary awareness, are very familiar with tsunamis, going back to the one in Santorini and so on, and 365 AD or whenever it was, I think it was, and of course, very much what people think about. And this is a sort of metaphor for this. And So, you know, so you can say the ingredients of the model, which we're sort of all arguing about the details, if you like, is earth, air, fire, and water, but this in an electromagnetic context. So this is strong magnetic fields are making radio waves of enormous intensity that we can see across the universe. So let me say a little bit more, again, now going from these two case studies, if you like, to talking about how astronomy is done. And this is particularly relevant to what Skinnikas Observatory is involved with. And this is modern astronomy is not just one telescope, one astronomer with a telescope looking with their eyes at the universe. Instead, it uses the whole electromagnetic spectrum, from the lowest frequency radio waves to gamma rays, all the way up. And you have got 10 grand pianos worth of spectrum there to play with. And most of this has been populated with telescopes and the associated instrumentation. It is this that has driven the explosive growth of understanding from astronomy. So you've just got one octave. That's all our eyes can see, is just one octave. And here we've got 70 octaves of electromagnetic spectrum, and most of those are accessible to astronomers. So here we have figuratively there, but we don't just have the electromagnetic spectrum. We have cosmic rays, I've already mentioned those. We have neutrinos, we have gravitational waves. Maybe we'll find other things in the course of time, but at any rate, we have these four messengers. Maybe we'll see dark matter one day. And so we go from the lowest energy particles to the highest energy particles, and you can say there's 140 octaves being explored. And so astronomers have got a lot to play with when they get to see cosmic sources. So I'm now going to change direction a little bit again now, having established that we can do this through multi-messenger or multi-wavelength astronomy. Let's just talk about the extremes. I said this was going to be, I'm working with extreme electrodynamics. I'm going to sort of try and impress you with how extreme these objects are. And I do this, I don't know, I suspect people in Crete have no need for Guinness, which is a term of beer that comes from Ireland originally. And they had a famous advertising campaign. This was all devised by engineers, curiously enough. And one of the parts of their advertising was to make a book called the Guinness Book of World Records. And it was to enable people to have arguments in bars who made the biggest or the brightest or the smallest or whatever of anything, or the fastest or whatever. And so there's the Guinness Book of World Records, and many scientists have aspired to be in the Guinness Book of World Records. I'm not sure anything has yet made it into it, but it should do. And I'm going to try and explain what the extremes are in the spirit of the Guinness Book of World Records. So a black hole merger, how much powers are associated with it? Well, at its peak, what they see and what they see with the detectors from a safe distance is 10 to the 49 watts. And I'm going to assume you know what this exponential notation means. It's 10 to the 49 watts. A gamma ray burst is tiny by comparison, a mere 10 to the 45 watts. That's an awful lot of light bulbs. An active galactic nucleus is a million times fainter than that. But this goes on for a long time. This only goes on for a second or so. So they're different in that regard. But still, here's an active galactic nucleus. So this gives you the frontier of power. If I go to energy, let's look at the energy of the particles that we're seeing. If we look at the neutrinos, using especially a detector at the South Pole called IceCube, but there are other detectors as well, including ones in the Mediterranean that are contributing a lot to this. You are seeing neutrinos with energies up to 10 to the 15 times the energy of, say, of an optical photon. These are called petaelectron volts, for those who know the electron volt unit of energy, which is used a lot in particle physics and nuclear physics. So these are enormously energetic particles, neutrinos, and they are made by cosmic sources. We have some ideas of where they're coming from, but my point here is how energetic that is. If we look at the gamma rays, these are the highest frequency take an optical photon and then just make it higher and higher frequency, you get up to gamma rays. These have energies, again, a million billion times that of optical photons, and they are seen by many detectors, especially one in Western China, in Western Sichuan, called LASSO, which is finding these very, very high energy gamma rays, extraordinary. And then I said the cosmic rays themselves go up to the energies of a well-hit tennis ball or soccer ball and football. Good. Here are two detectors that are one in South America, one in Utah, and they are seeing these very high energy cosmic rays. So again, these are the extremes of energies of the particles that you are seeing. If we take temperature as a measure, then if we go into the interior of a neutron star, when they're made, they have temperatures of 10 billion degrees. And in fact, you may think of 10 billion degrees as rather hot, but in fact, in the context here, it's really rather cold. And you can still do at slightly lower temperatures, you can still do superfluidity and superconductivity. It's that cold. So it is cold, so you see temperatures there. If we go to these fast radio bursts, remember I said these fast radio bursts that were seen, and they last maybe milliseconds or microseconds, and we think they're associated with magnetars. What we can say, for those of you who know the black body formula, the physics students who know the black body formula, we can associate a temperature with them. It's essentially the amount of energy in a cubic wavelength, and that will be about 10 to the 40 degrees Kelvin using exponential notation. 10 to the 40 degrees Kelvin. And you might say, well, that's a lot, but if you tried the same game for a tsunami, and it's obviously water waves, not electromagnetic waves, you'll get about 10 to the 35 Kelvin. So a tsunami is about the same temperature. And in some models, it may go up to 10 to the 60. So this is hot. Okay, so this is the thermal frontier, if you like. If we go to the frontier of observation, then here are just some of the telescopes we're having or using at the moment. I've already mentioned some of them. Here's James Webb Space Telescope, which has been an extraordinarily successful. It's miraculous that it all works, and it works extraordinarily well. And it has taught us so much about the universe. That's part of the story. Here's X-rays from the IXPE. I showed you the polarimetry from IXPE. Here's a facility that's just coming online. It's going to look at half the sky every 4 days. It's called the Vera Rubin Observatory. Here's a radio telescope, and another one that's being built. This is one that exists and one that's being built in a few years. That's going to look at the fast radio bursts and much else besides. Here's LASSO and IceCube I've already mentioned. Here's the Event Horizon Telescope that made that M87 image. This is telescopes all around the world. And here is an X-ray telescope. Here's Kylafis. And Kylafis can play a very large role in this in two ways. One is it can do the very fast turnaround. I've seen the telescope move. It moves extraordinarily fast. And you've got an alert for a gamma ray burst, and that lasts a second or so. You've got a second or so to move that telescope to see what happens next. Kylafis is one of the few telescopes that can do that. And the other thing it can do, and Vaso and others have been working very hard on this and had a lot of progress, is they can look at the polarization at optical wavelengths. And this, again, is a great capability which you can use using Kylafis. So I'm very excited about what will come here. Here's now a telescope that's been up for about 9 months called SPOM. Again, she's telling us about gamma rays and X-rays. So there's a lot going on, and there's more coming over the next few years. So there's a lot of discovery out there. Let me say a little bit about the frontier in observation. Here's the sky seen in gamma rays. Here's the sky seen in neutrinos. Here's the sky, if you like, seen in cosmic rays. And if we look at the universe and we look at the scale measured here to the highest energy cosmic rays right up here to about the energy of a proton and so on, we find that the universe is, if we try and look right across the universe, we are opaque. It becomes cloudy after a certain distance out into the universe, and so it's opaque to photons, but it is transparent. This part can be transparent to cosmic rays and neutrinos. And so the cosmic rays and neutrinos, particularly those of high energy, can tell us about the universe at some distance, especially the neutrinos, where we can see right across the universe. Gravitational waves can do the same. And so we can look right out at the sources right across the universe. And so that's, again, a great benefit, just like we do at optical wavelengths. So that's an observational frontier. And then cosmology, the study of the universe at large, is being greatly enriched by this sort of extreme electrodynamical sources, the black holes and the neutron stars. These black holes and the nuclei of galaxies, they make them active, and they aren't just sort of passive things that happen there, they are active. And what they do is they mediate the formation. It's becoming increasingly clear that they are mediating the formation of galaxies and stimulating the formation of other galaxies. And instead of just being sideshows, they are in fact prime movers of galaxy growth and evolution and formation. Here's the coalescing, the merging neutron stars. Remember I said 2 neutron stars came together and were observed as gravitational waves. These, when you get these 2 neutron stars coming together, these are sources of many of the heavy elements that we see around us. This is where they come from. For a long while, it's been a big puzzle where a lot of the heavier elements that the chemists know all about, where they actually come from. Now we have a good working hypothesis that this comes from, much of those come from neutron stars. Not all of them. It turns out that if you like jewelry, the good stuff, the platinum and the gold and the silver and so on, that comes from this source. The cheap stuff, the zirconium and so on, that comes from other places. So this is the good stuff that comes from these merging neutron stars. We can use them, as I said, the fast radio bursts can be used for measuring where all the gas is in the universe, and there's been a lot of progress in the last year on that. And then the gravitational radiation, perhaps from merging black holes, that is also being seen using pulsars. So there's a lot going on here, and it's all interconnected. It isn't just one separate problem and another separate problem. The whole thing is all connected together. In trying to understand this, and this is what my colleagues and to some extent I do, is a lot of this is done using computational methods. As I said, these are now very hard physics problems because they involve plasma physics, they involve many body physics, they are very challenging. You can't just do this with a pencil and paper. And so a lot of work is done, happens doing simulations. And so you try and understand how much very strong magnetic fields and the associated plasma behaves in a series of experiments that have taught us an awful lot. And increasingly, we're doing experiments. So we're doing experiments with beams of electrons and in some cases protons, and especially beams of X-rays and other sources of radiation. And using the same sort of simulation tools, you can try and get an understanding of the physics under these very challenging circumstances. So that, again, is one of the sort of frontiers of this field. And here are some of the experiments that are shown. In fact, I've just been on calls earlier this week on experiments I was associated with that is producing interesting results. And we can use these laboratory facilities to probe analogs of the physics that happen in these distant cosmic sources. And now if we go back again to the electromagnetic frontier, here's the magnetar. This is actually a numerical simulation with magnetic field lines coming out of it, an instruction in the interior. Here's more of a cartoon of a spinning neutron star with a disk of gas orbiting it and a huge magnetic field crossing its surface. In this case, in the case of a quasar, in terms of voltage, there would be 10 to the 20 volts across the surface of the black hole. And if we go to something like a magnetar or gamma ray burst, perhaps, there might be 10 to the 23 volts. That again is a lot of batteries. So these are enormous extremes of electromagnetic quantities. The currents are similarly large. Here's the magnetic fields. let's say, just to emphasize again, in the interiors of these neutron stars, they could be as high as 10 to the 17 Gauss or 10 petatesla, 10 to the 13 Tesla. And again, we have to understand the plasma physics to get a handle on this. So how am I doing for time? 5 minutes? Okay, so what I have is I'm going to finish this off with what I regard as 3 top-level questions. These are ones that if one looks at the physics with the broadest of brushes, not the sort of smallest of microscopes looking at the very tiny levels, but instead just trying to get the big picture. And so the first one is, what are the main pathways for these cosmic sources? I've fenced at this problem just a little bit here, but let's get practical. If we look at sources like that great orange donut in the sky, the ring in the M87 galaxy with the shadow of the black hole there, what is actually powering all of that? One possibility is that there is gas that is supplied to it that is falling onto the black hole. And just like Newton's apple falling from the tree when it hits the ground, it loses its kinetic energy at the expense of the potential energy, and then that all goes into heat. The same thing happens in gas spiraling around a black hole. As we supply gas, it falls in, crosses the event horizon, and it releases energy and glows, in this case, for the gratification of millimeter wave astronomers. That is one metabolic pathway. It's not the only one. Another one is that the whole performance can be powered by the spin of the central black hole. And the gas is in some sense only incidental. Its only job is to keep the magnetic field in place. And really all of the power comes from the spin of the black hole. That's a qualitatively totally different idea. And sorting that out is something that I think we will do in a relatively short space of time. To give you an analogy to what I'm talking about here, in the 19th century, astronomers had a rather good theory of the sun. They said that the sun was powered by gravitational energy, a bit like Newton's apple falling on the floor, on the ground. And a natural consequence of this was the sun should only be about 10 million years old. And by extension, the planet should only be 10 billion years old. And it then became clear that the Earth was 1,000 times older than that, roughly. So it was 1,000 times older than that. And so to cover their embarrassment, physicists and astronomers and geologists had to invent another source of power, which was, of course, nuclear reactions. And so they developed a theory of the sun that where it was powered not by gravitational energy, but by nuclear energy going on in the center of the sun. So there was a qualitatively different source of energy. And that's the debate that's going on here. And so finding out in these different sources, is it gravitational? Is it rotational? We know, in some cases, we know the answer, but many we don't. Is it electromagnetic? In the magnetars, they are spinning rather slowly. The energy there, we are pretty confident, comes from magnetic field, not from rotation, not from nuclear processes, but from magnetic field. It's magnetic field that is releasing the energy. And in some cases, like in supernova explosions, it's the neutrinos that are carrying the energy away. So there are big questions here, and this is a top-level question to try and sort this out. And my suspicion is, and my hope is, that it won't be too long before most reasonable people will agree on what the answers are. Let me go to the second one. I emphasize the extraordinary energies of individual particles, the cosmic rays with the energy of a well-hit tennis ball. How does nature perform this trick? We struggle at the Large Hadron Collider in Switzerland. We struggle to make protons hit one another with energies that are 1 million times less than this. Okay, so it's a how does nature perform this trick? How does it make these highest energy cosmic rays? And no less challenging are the neutrinos and the gamma rays. That's something we need to do. We have lots of theories for how nature performs these tricks. I suspect only a few of them are actually operating, and we will learn through a combination of calculation and especially observation, and to some extent experiment, we will learn if they're right. And there's a possibility that there may be some quite exotic things going on, but there's no need for that right now. So that's the sort of second top level question. And my third top level question is there a need for new physics? Physicists are always, they're greedy. They should be satisfied with the wonderful physics that has been discovered by their predecessors, but they keep on saying, I'm going to discover more new and exotic and different physics, qualitatively different physics. They're eager to do this all the time. Now, is there a need for this? Is there any evidence for physics that goes beyond standard electrodynamics? Remember, I distinguished classical electrodynamics, the electrodynamics of James Clerk Maxwell, and the quantum electrodynamics of Richard Feynman and Schwinger and others together. Do we need some new qualitatively new physics or not? Now, my view, I'm what is called, I think, a reluctant conservative. This is an old phrase, a reluctant conservative, in that I have to be dragged to new physics unless there is evidence for it. And so my expectation there is no physics, but by being a reluctant conservative, I hope so much that I am wrong. So what I want to be is wrong about that working hypothesis. There is, I think, no evidence for it as yet. Black hole event horizons, axions, and so on. For those who know what axions are, these are real opportunities for finding new physics. But there's as yet no evidence for it, but we're all eagerly on the lookout for something that doesn't fit that might be an indicator for that. So that is the new physics. That's my third top level question. And so that's part of the excitement of this general field, as I say, is moving forward very fast. And so lastly, let me just give a summary here. I would just sort of say that there have been remarkable observational discoveries that have taken classical electrodynamics and quantum electrodynamics into extreme regimes. A lot of this is being facilitated by multi-messenger astronomy. That's using these 140 octaves, not just the one we can see with our eyes. Most of this exotic stuff, this extreme electrodynamics, involves these two structures, neutron stars and black holes. We have very large numbers here, 10 to the 40 degrees Kelvin. That's the mass of a massive black hole. These enormous magnetic fields, which we've got evidence for, and maybe even more than that, enormous voltages, enormous temperatures, enormous powers, energies for gamma rays, neutrinos, and cosmic rays. We've got these wonderful objects that we're sort of beginning to understand how they work and use them. Quasars, pulsars, gamma ray bursts, the ultra high energy cosmic rays, magnetars, supercharged magnetic fields in pulsars, flash radio bursts, very high energy neutrinos, the gravitational wave background. These discoveries are happening. Many of these are new recent discoveries, and there will be more over the next few years. There's opportunities for new fundamental physics, but nothing so far. And there's a sort of methodology here, which I've tried to sort of illustrate. When there are new discoveries like this, there is a crazy list of possibilities out there, but this is a progressive business, this science. And very quickly, most of those wither away, and you're left with 1, 2, or 3 explanations for the whole thing that you're using. And there's a lot of progress right now, which makes it very exciting. And then I've sort of just hinted a little bit at this. There's a sort of 2 ways of doing science, if you like. There's the bottom-up way, where you sort of build things up from the most fundamental, elementary parts, and then you try and make more of them work together. And then there's a top-down way, which is, you say, you look at the largest structure, you look at the most meteorological, if you like, of the phenomena, and then you try and infer what's going on the small scale. And in this type of science and many others, you do both. Sometimes you're working from the top down, sometimes you're working from the bottom up, and you're always trying to make the two agree and reconcile them with what you observe and measure in the laboratory. And so it's an exciting time. It's a time of great discovery, and who knows where it will lead. Thank you very much for the honor of giving this talk and helping us.
Thank you very, very much. Questions for Professor Blandford?
There's one thing which
So one type of detector you didn't mention at all, which is the gravitational wave detection.
Yeah, I didn't mention them. Yes, I should have. With more time, I sort of showed. I alluded to them. Yes.
So how do you think? What role will they play in this in the discovery business?
Considerable. I mean, my topic was really electrodynamics. The LIGO detectors or the LIGO type detectors are microscope interferometers using lasers, and they have been detecting mostly the mergers of black holes, and they haven't been seeing electromagnetic displays associated with them. They have seen in one very famous case, two neutron stars merging together. Those should be electromagnetic displays. And that's, we're looking forward to more examples of those where we may be able to catch them doing extreme electrodynamics. But so far, they're mostly viewed as purely gravitational phenomena. So that's why I did not quite emphasize them, but I'm excited about the future possibilities there. The place where the pulsars come in indirectly is measuring this gravitational wave background from the timing of the pulsar pulses. As you get the timing of the pulsar pulses, that allows you to detect the gravitational wave background. And that's a sort of indirect use of those pulsars as tools rather than as objects of interest in their own right.
Yeah.
Is it known why some neutron stars have very strong magnetic fields and others less?
For most of us, the answer is no. Some people do believe they understand this. I think the rest of us don't. I think it's pretty clear that there are possibilities of making these strong magnetic fields, the 10 to 15 Gauss, and they're almost certainly associated with young neutron stars. And by young, that means within maybe a thousand years of their formation. And what happens is when the gas in the center of the star collapses to neutron star density, if it stays as a neutron star, which it doesn't have to do, but if it stays as a neutron star, it will be extremely hot. There will be neutrinos and so on, and there will be lots of thermal overturning. It will not shock you to know that that will lead to some turbulence. This is extremely conducting material, so magnetic fields go along for the ride. And if we put magnetic field in this turbulent, overturning nuclear matter, you're going to make an enormous magnetic field that will only stop when the forces associated with those magnetic field lines oppose the overturning motion. And that can take you easily up to 10 to the 15 Gauss. Details, some of my colleagues believe they understand what is going on. Others are not so sure we understand, like me, are not so sure we understand that, but it is very much an active area of investigation. And you asked exactly the right question. So if you have the right answer, please come and see me afterwards.
Other questions?
This is a question about the strong magnetic and electric fields. You showed them the extreme temperatures. First of all, the evidence for these numbers is experimental, right?
Well, observational in most cases, yes.
Yes.
Mhm.
Okay. I wonder if you mentioned already that there is no drastic new physics you are aware of. But nevertheless, I wonder if there are some scenario about, for example, having some sort of quantization of space-time due to these extreme conditions.
Well, the notion that space-time is in some sense quantized doesn't actually require the electromagnetic field, because various forms of quantum gravity have implicitly that view that space-time is quantized, and of course that is very much a work in progress in terms of making a theory. The interaction of theory, if you like that, is enriched by putting strong magnetic fields there, especially ones above this famous Schwinger field, and that would certainly enrich that in some expressions of quantum gravity. Yes, so there is a possibility there, but there's nothing that's screaming at you from the observations that's saying this has to be going on, but it would be lovely to find it.
Is there some perspective to observe that in the foreseeable future? Possibly with new satellites, for example.
Yeah, no, I hear you. There is this is discovery. I mean, astronomers, most of the things that I've told you about here, and I could have given lectures on other subjects, most of the things happened using telescopes or facilities that were designed to do something else. Astronomy is very much a discovery-rich subject. Now, you can interpret this as saying that astronomers don't know what they're doing. And at some level, that may have some truth to it. But I will say something for my colleagues, especially the observers, is that even amongst distinguished scientists, they're extraordinarily good at noticing what doesn't fit and then going on to sort of figuring out what lies beneath it. And one of many examples I showed you was almost the first slide, was Jocelyn Bell discovering pulsars. It was something that didn't quite fit. And, 9 out of 10 people would have just sort of walked away from it, but she didn't. And she made a fabulous discovery. And there's a lot more examples of that sort of thing. So that can happen. Now, if you ask me to put my finger on something just as a conjecture, as a hypothesis, a hint or a hope, there's a small possibility, if you're going out into new physics, of axions being made manifest in the magnetospheres around magnetars. Now, how that's going to express itself, I don't know, but it's not a bad place to think and look. So that would be one example. The things associated with quantum gravity and so on, I see as being much harder, a much harder challenge for astronomers.
Okay, thank you.
Other questions? Achillea?
What part of the extreme electrodynamics gets even more extreme if there is an extremely rotating black hole around?
What part?
Which parts of the extreme electrodynamics you discussed are getting even more extreme if there is an extremely rotating black hole nearby?
Well, what is more extreme than an extremely rotating black hole? Well, it depends how you look at extreme. If I say in terms of voltage, it's pretty extreme. If I say in terms of strength of the magnetic field, the massive black hole in this M87, for example, this orange donut in the newspapers, that is only about 100 Gauss. It's not very much. You get much more in an MRI machine. So it's not very much magnetic field. That's not extreme, but the voltage is large.
Sorry, my question was about extreme spin. So suppose the black hole is spinning extremely fast, as it can.
I misunderstood.
What gets more interesting?
Yeah. Okay. There's a limit to how fast the black hole can spin. And that is implicit in the mathematical description of a spinning black hole that this New Zealander Roy Kerr found. And that basically says that the amount of spin energy can be no more than 30% of the E equals mc squared energy of the black hole itself. based on its mass. And so that's the limit to how fast it can spin. And if you say it's spinning close to its maximal rate, then you've got a lot of energy to tap using magnetic field to power the jets and all the other parts of the show. Similarly, with neutron stars, there's a maximum spin energy you can have. We don't quite know what it is because we don't know quite what the structure is. And we're learning a lot about nuclear physics from them, I'm sure. But it would be something like about a millisecond would be about the fastest spin you could imagine, maybe a little bit less than a millisecond. And beyond that, the thing would just blow itself apart, everything would just fly off. So that's the maximum speed. So if you found a pulsar with a spin, say, of 100 microseconds, a spin period of 100 microseconds, then we'd all be scratching our head. So there's a maximum spin energy for both neutron stars and for maximum spin rate for both neutron stars and for black holes. And that's a prediction, if you like.
Follow up by Elias.
Let me qualify a little bit the question before. Once you have a black hole that is maximally spinning, as you're saying, in this case, if you follow the plasma that can be rotating near that black hole, you may be getting into a kind of extreme plasma dynamics. Is it understood?
The second question is no. And again, a lot of us are working hard on that. There's, some aspects of it I think are understood. So let me go into something slightly technical, but it will be, to those who are physics students, they will get it. If you imagine electromagnetism as presented, originally the Maxwell theory was there in the context of Newtonian physics. But as most physics students quickly get to learn, it actually fits in very nicely with the special theory of relativity. And if you use the special theory of relativity version of Maxwell's equations, you find there is a quantity which is the difference of the square of the magnetic field and the square of the electric field. And what's special about this is it's the same however fast you're going. It's what's called a Lorentz invariant. That's the fancy name for it. And it's the same in all reference frames. Now, that's a quantity that can be either positive or negative. Under most circumstances, around here, it is positive. However, in these magnetars, in aspects of the quasar stories I've been telling you, it can become negative. At that point, electrodynamics changes, not in a way that's new physics necessarily, or new fundamental physics, but certainly new physics in terms of the way it's expressed. That's a really big difference that can happen. And in these extreme electrodynamic objects, you have to confront the evolution of a system that has the magnetic field strength larger than the electric field strength to one in which that ordering is changed. Then what happens next is totally different. That is very interesting and maybe strongly connected to many of the objects that we're looking at, including the fast radio bursts and the flares around black holes.
Any more questions? Well, if there aren't any more questions, let us thank Professor Blandford very much again.